was the best MP. Just
He
a
really,
wonderful man.
well, whenever you like
Oh,
to,
we're starting? Okay, you're just holding a spare. Ask me a leading question to
Well,
start off.
where you were born and grew up, and
Okay.
what your parents did.
Okay. I was the youngest of 3 children. My parents were immigrants from Austria or Poland, depending on the year. My father had gotten through high school. My mother died illiterate, but they both valued very highly education for all of the children. I was the youngest. And in Detroit, I naturally went to what was then Wayne University before it became Wayne State for my undergraduate work. I had the good fortune of having as my P-Chem teacher in the senior year a person who himself had been, who himself had been a graduate, a PhD from the University of Chicago, and encouraged me to apply to Chicago, which is one of the first fortunate things that ever happened to me. And I remember being called out of P-Chem class one morning in the spring of 1938. My father was waiting for me at the university in the chemistry department. And he was bringing joyous news from home, which had just arrived in the mail. I was accepted at Chicago and was offered the Eli Lilly Fellowship, which it turned out to be a whole tuition scholarship of the total of $300 per year in 1938, which covered all the tuition. So I ended up at the University of Chicago. Wonderful place, then, still is. And as is the case for all graduate students, you have to decide on your PhD thesis advisor, your mentor. And I chose, because of the man, not the problem, James Franck as my advisor. He was already a Nobel Prize winner in physics for the first experimental demonstration of the accuracy of the Bohr theory of the atom. But he was interested in the interaction of light and matter. And the most important photochemical reaction, of course, is photosynthesis, by biological reaction. But he ended up in the Department of Chemistry just a year, I think, before I came to Chicago, sponsored by externally for a program in photosynthesis. So I ended up with a physicist working on a biological problem in a department of chemistry at Chicago. And all of these things were useful to me in later life. My test system, actually, was a green algae, chlorella, and the kinetics of photosynthesis as a function of light intensity and also of selective poisons for the enzyme systems. Anyway, I got my PhD from Chicago and a lifelong role model from Professor Franck, who not only was a distinguished scientist, but in my eyes still one of the most noble human beings I ever encountered, I must say, along with Paul Emmett. After Chicago, I did a postdoc at NYU with Milton Burton, who was interested in the fact that molybdenum was said to be important as a trace element in the enzyme responsible for fixing nitrogen in the bacteria in the roots of legume plants. After that, I returned briefly as a research associate in photosynthesis with Franck, but shortly after that, into war research. Fortunately, I was only 22 when I received the PhD, so as a PhD, I was able to do constructive things on, I hope, problems associated with the war effort. First of all, at Chicago and Northwestern, in an attempt to modify the surface chemistry of activated charcoal, which is used as the adsorbent and the base for other impregnants in gas masks, and with very interesting results, which I was able to publish after the war and get declassified. But during that period, I first met a second savior, Paul Emmett, who was in charge of the branch of NDRC responsible for the research on charcoal. Subsequent to that, in 1943, I transferred to the Manhattan Project, oddly enough, in Manhattan. And there I had interesting supervisors. My direct supervisor was Bill Libby, who afterwards was himself a Nobel Prize winner after he came up with radiocarbon dating. And his supervisor in that effort was again Paul Emmett. So again, I had contact with Paul. Well, my work on the Manhattan Project really was concerned with thermodynamics of the uranium fluorine system. And we discovered actually a new intermediate uranium fluoride, which ultimately was the subject of a patent after the war also. U4F17, a black material but crystalline. Anyway, after the war formally ended, I ended up at what was then the U.S. Bureau of Mines in Pittsburgh on the synthetic fuels program, headed by Henry Storch, again a wonderful guy who indulged me in all kinds of my own foibles and not willing to do what he suggested and permitting me to do what I was interested in. I spent my initial year or two at the Bureau of Mines, which is now the Pittsburgh Energy and Technology Center of DOE for many years now, doing my own bench research on the Fischer-Tropsch synthesis. And then I was offered the position of being assistant chief on the coal hydrogenation effort, direct hydroliquefaction of coal. And a co-worker of mine, Mike Pellepetz, who has been dead for decades now, and I did pioneer work, which was easy to do at that time because hardly anybody was working on coal in a serious way. On the kinetics of coal liquefaction with intermediates, and on the role of catalysts in liquefaction. Well, toward the end of 1949, 1950, it was becoming clear to me that the prediction that everybody would run out of petroleum in 10 or 20 years was not going to be fulfilled with the discovery of new fields. And also, I was interested in getting back to a more intense study of catalysis. I fortunately was interviewed at an ACS meeting by the noteworthy combination of Alex Mills and Alex Oblad at Houdry Process Corporation. And I went there. I spent 8 happy years at Houdry. For the first 7 as head of the fundamental research section. And at that time, it was possible to devote for my group perhaps 80% of our time in doing what I considered to be as fundamental research as I knew at that era on basic problems in catalysis, and 20% of troubleshooting or firefighting or whatever. During the last year at Houdry, the fundamental research was downgraded or abolished. In 1957, there was a recession, and I was put in charge of the effort on the chromia alumina dehydrogenation catalyst for the butane to butadiene process of Houdry, which was indeed very interesting, but limiting for me. So I finally decided, because of the limitation on seeing the country and the limitation on the weeks of vacation time allowed after 15 years of effort or something, that I would explore other possibilities. And I ended up at a division of the Ford Motor Company in Southern California, Newport Beach, moving there from the Philadelphia area. For the first month or 2, I was made manager of propulsion research, which means what goes on in a rocket, at which time I amused myself by saying to myself, I had to learn which end of the rocket was back and which was front. One is closed and the other is open, of course. It was much more sophisticated than that, but anyway. I spent 7 years there with some change in management, in the sense that the aeronautics division of Ford became Philco Ford after Ford made the mistake of buying Philco Corporation. But by the end of 1965, I was director of the chemistry research laboratory and acting manager of the materials research laboratory for Philco Ford both at Newport Beach and the residual labs, mostly electronic, located in Philadelphia. By that time, I was disillusioned, I would say, about doing, quotes, defense work, which mainly meant offense work, and jetting from Los Angeles to Washington and back, and seeing what contracts could be obtained, mainly from DOE at the time, DOD at the time. And Ford had paid me well enough for my position so that I could afford to indulge a long-standing longing to get into academic life. And through a good friend at Caltech, former president of AICHE, now dead, I got a call at my desk in Newport Beach from a man I didn't know, who was the chair of the new Department of Chemical Engineering at the State University of New York at Buffalo. And we arranged that he would come down from the AICHE meeting in San Francisco, and I would go up to Los Angeles, and we rearranged to meet at the airport. He invited me to come to Buffalo and for an interview, and 2 weeks later I had a written offer to come as full professor at Buffalo. And I must say, it was one of the most rewarding experiences in my scientific career. I spent 24 years teaching there, starting at age 47, which is pretty old. Finally retired at 71 in 1989, and was fortunate to be a visiting fellow later that year at Oxford University. During that period as an academic, I was very fortunate to be able to travel, always as an invited guest, and honored guest, I must say, to fairly exotic places like Istanbul and Australia and China to lecture, and twice as a Fulbright in different years lecture. Let's see, where do I stand now? During that same period, fortunately, I received some 3 ACS awards, national and local, and finally a Dean's Award from Buffalo for engineering achievement, which also struck me as funny, because I didn't really consider myself an engineer, having graduated in PChem from Chicago. And I didn't see that I had achieved anything either, but like all awards, they're nice and never turn one down if offered. So since then, I didn't know how long I would live, retiring at 71. So I decided to not take any more PhD students. I maintain contact with many of my former students, some of whom are here. But it's been amazing to me that I have, through last year anyway, sort of cranked out papers at almost the same rate as I did during the active years as a teacher, and fairly knew two review articles, one on kinetics and one on coal, and a chapter in a book last year. But I find myself more and more intrigued by an old passion dating from my undergraduate years at Wayne. Having run out of all the chemistry courses they offered, it turned out that one of the faculty members, who was not a research man but offered a course in history of chemistry that I took and found intriguing. There are all sorts of things in the background of chemistry which tend to be forgotten, like the theories of phlogiston or caloric or affinity and so on. So I find myself increasingly intrigued by special topics in the history of chemistry which have to do with long-standing professional interests of mine. For instance, in chemical engineering, we have occasion to be interested in the conditions that operate at the entrance and exit of a stirred flow reactor which is non-ideal. And credit for the proper conditions are attributed to an Englishman who published these in the 1960s. The same conditions, the same math was published by Irving Langmuir in 1908. Decades earlier. Langmuir is one of the intriguing figures in, I would say, physical chemistry. He started life with an undergraduate degree in mechanical engineering, did his PhD with Nernst in Europe, came back to teach undergraduate chemistry in a department of which he became the third of three faculty members. It was not very rewarding for him, and after about 2 years he was attracted by the new GE laboratory just being set up there. While still during this 2 years of teaching, Langmuir published this study in 1908 at a time when the same year the AICHE was just being organized. And I paged through the first 5 or 6 volumes of the AICHE transactions. There is not a hint of the math involved in Langmuir's treatment of flow reactors. And there is in Langmuir's paper non-dimensional combinations of parameters that were given names attributed to other people over the decades. And I was interested in tracing this back because the same dimensionless parameters were listed in some AICHE compilations published in the 1960s. And I followed the references for those parameters, the references going back, and each of the preceding references referred to some earlier reference, and the final reference was a German article which Langmuir quotes in the same year, 1908, which doesn't have any math at all. So a small article on Langmuir I published in the Chemical Engineering Education a couple of years ago. Meanwhile, since kinetics has been a long-standing area of interest for me since my start in the kinetics of photosynthesis way back in the late 1930s. I became intrigued in looking up the origin of the law of mass action, which has been conventionally attributed to the Norwegians Goldberg and Vaga, who published in 1864 in Norwegian, and then 3 years later published in France, but still in French, but still published in Norway, and more or less ignored even at that time until their final publication got the law of mass action correct. The first two had it wrong in detail. In 1879, by which time both Van Hoff and Ostwald had deduced the proper form of law of mass action for reversible reactions, and I guess that Goldberg and Vaga were afraid by 1879, when they finally published in German, in a German periodical, that their earlier work was being ignored and perhaps forgotten. Meanwhile, there is a lot of background before 1864. I won't go into many of the details which continue to intrigue me, but I will mention some things. One of the outstanding concepts in writing down the law of mass action is there is for reversible reactions a forward rate and a reverse rate, and finally equilibrium is reached when the forward and reverse rates are equal. Where does the concept of equilibrium enter into chemistry? Not until the end of the previous century. And that is totally fascinating to me. Not so much for the chemistry, which is interesting enough, but for the historical aspect. One of the most distinguished French chemists of the last half of the 18th century was Berthollet, who at the age of 50 ended up as one of the most trusted advisors of Napoleon Bonaparte, who was 20 years younger, and according to the information I have, tried to teach chemistry to Napoleon in Bonaparte's spare time between the Italian campaign in 1796 and the campaign into Egypt, 1798. He was asked by Napoleon to round up some 15 scientists and mathematicians to accompany the expedition to Egypt, which he did. While in Egypt, he accompanied a general in the army to a series of salt lakes. There is in Arabic something called Wadi el Natrun, or Valley of Soda, northwest of Cairo and somewhat halfway between Cairo and Alexandria, where there are on the shore of the lakes enormous deposits of soda, sodium carbonate, which is something that was very important in France and all over at the time. Anyway, there was supposed to be a reaction, according to the theory of affinity, between sodium carbonate and calcium chloride. There were limestone cliffs around the lakes, which are below sea level, actually. And the reaction is supposed to go, according to the theory of affinities, to completion, calcium carbonate and sodium chloride. Berthollet, who was a very able chemist, took upon himself the job of analyzing the water in the lakes and discovered reactants still in the lakes. How come? He says to himself. He says there is an equilibrium, and instead of reactions going to completion always, the rate of reaction, or where the equilibrium ends up, depends on the relative masses of the reactants and products. So we have, for the first time, published by him in Egypt, in a lecture in 1799, and after that in France when he returned in 1801, the introduction of the whole concept of equilibrium in chemistry. I didn't know that or anything about it. Now, toward the end of his life and the life of the astronomer and mathematician Laplace, they were friends, lifelong, and ended up living in the same suburb of Paris. And they organized a scientific society. They too were the older senior members, and they organized some 10 younger people and formed a society which met regularly to discuss scientific problems. The younger people included, for instance, Gay-Lussac, Alexander Humboldt, who lived in France for some 20 years, the physicist Biot, or Biot, and others who became famous afterwards, but this was the early training. Gay-Lussac, incidentally, was earlier the assistant to Berthollet. Well, Laplace. I became interested in Laplace because he shows up in this story. Laplace was also a senior advisor to Napoleon, also 20 years older than Napoleon, and very trusted. All of these guys, especially after the Egyptian campaign, were made senators by Napoleon and made counts by Napoleon. At an earlier stage, Laplace, it turns out, was recruited. Laplace published a 5-volume treatise on celestial mechanics, very famous, and 2 volumes on the theory of probability, very famous. But he was recruited by Lavoisier, And they worked together for some 2 or 3 years on the nature of heat. And they published a small book on this, of which our library has a copy, and I went through. I have been going through and slowly translating article after article of the original publications in French. Fortunately, I had as an undergraduate for a whole year, but it's been useful. Now, Laplace, having worked with Lavoisier and then become ennobled by Napoleon, was an astute politician. Another really good mathematician and chemist, contemporary of Berthollet, named Monge, M-O-N-G-E, was similarly made senator and made a count by Napoleon. Monge, at the end of Napoleon's career after 1815, was what I would call a survivor. I'm sorry, Monge was not a survivor. He stuck by Napoleon throughout, defended Napoleon and so on. When the Bourbon Restoration occurred after 1815, Monge lost all his honors and the position as count. So he died in relative obscurity. Laplace not only stayed as president of the Academy already at that time, and of the Senate, and as a count, but was made a marquis by Louis XVIII after the restoration of the Bourbons. So we have a concatenation of people. Lavoisier, Laplace, Berthollet, each with their historical history, aside from what each did scientifically, that distracts me from the mathematical treatment of somebody I haven't come to, also a predecessor of Goldberg and Vaga. 2 generations later, another Frenchman, Berthelot, with Pasteur, probably the most famous chemist of the last half of the 19th century. In 1861, 1862, made an enormously detailed study of the rates of esterification of various carboxylic acids with the various alcohols, ranging from ethanol to acetyl alcohol, from sperm whales, spermaceti. But the prime example is what you or I would pick, acetic acid plus ethanol. And the experimental work was carried on during long periods, 6 months experiments or 1 year experiments, at different temperatures, ranging from the cellar, or cave in French, which Berthelot describes as varying in temperature from 5 to 8 degrees Celsius. Room temperature, or ambient temperature as they call it, which I will come back to, 85 degrees, 100 degrees, and some temperature above 100. The room temperature experiments, Berthelot refused to use in his theoretical, it's blinking,
Yep.
whatever that means. Do you want me to halt for a minute?
Just a second.
Experiments of Berthelot and Saint-Gilles, who did the experimental work with him, were never used by Berthelot in his own workup, the theoretical workup of his own data, but were used, and only that was used from one run by Goldberg and Vaga with their treatment. Apparently, Goldberg and Vaga's results were used by Van Hoff afterwards, by Nernst in his text on physical chemistry afterwards, and as far as I can make out, nobody ever bothered to read the French originals, where Berthelot explicitly mentioned that during long runs, which maybe ran from January to August in a year, the temperature of the room, the laboratory, varied as much as 25 degrees. Now, we're supposed to apply the law of mass action quantitatively to isothermal data. This is hardly isothermal, and nobody has noticed this at all. Well, without going into the mathematical details, Berthelot, on his own, in the third of three very long papers, adding up to some 160 printed pages, ends up with a rate equation for a second order reversible reaction, which reads very much like what is rigorous and rigorously correct for first order, that the rate for first order anyway is proportional to 1 minus the amount converted, x, over the equilibrium conversion. So 1 minus x over xe. For second order, by wild reasoning, which I won't go into, Berthelot ends up with the rate of the second order reaction is proportional to 1 minus x over xe quantity squared, which looks plausible. Not only does it look plausible, but for fitting his own data, particularly for the one reliable temperature, 100 degrees, which you can thermostat even in 1862 by boiling water, fits very well. And the Goldberg and Vaga treatment, which is what you find in senior texts in chemical engineering kinetics, doesn't fit what's going on. So I have been exploring what other people have done in, first of all, looking in detail at the mathematical treatment of Berthelot, which has been ignored ever since Goldberg and Vaga, and what other investigators may have done on other systems since then. And if I live long enough to put down the historical romance that I was describing with Lavoisier and Laplace and so on, and Napoleon, and the math involved in the detailed fitting of experimental data, I will decide what to do. If I ever write this down in understandable and readable fashion, my guess is there is no possible source of publication, either journal or publishing company. But I'm having fun, and at my age, what more can I ask? That's it.
Well, how about going back to the Manhattan Project?
Yeah.
What did you do with Libby? What was your task?
Well, I don't know if I was even assigned this, but anyway, I ended up studying the phase diagram it comes down to for uranium and fluorine. The common phases for uranium fluorides are +4, +5, and +6. Uranium hexafluoride is a vapor, enormously water sensitive to hydrolysis, and important in the diffusion process for separating isotopes. So I had the job of constructing, which I did with my own hands, and a vacuum apparatus out of metal with necessity to weld things instead of glass blowing, which I had done during my graduate student days at Chicago. And discovering the intermediate phases which might occur. I thought we had two previously unknown phases, besides U4F17, U2F9, both between the +4 and +5 valence state of uranium. Turned out that the U2F9 had already independently been discovered by a separate group in the widespread and poorly communicating Manhattan Project. And the crystal structure had been worked out by distinguished X-ray crystallographer in the physics department at the University of Chicago, Zachariasen. The time that I came up with the U2F9 phase, I went into Bill's office quite excited, telling him about this. And he was not an experimentalist. He was one of those people whom his students described: when he opens the door of the laboratory, glassware breaks. But he was marvelously inventive. So on the spot, on the blackboard, he invented the crystal structure of this intermediate fluoride, U2F9. I was very impressed. Turned out to be exactly wrong when Zachariasen published the determined crystal structure. I'm not sure that Libby, who thought very highly of himself his whole life, was ever bothered by this kind of thing. But a wonderfully smart guy, nevertheless. So day to day, I had no contact with Libby. And Paul Emmett was a saving grace for me anyway. Something I forgot to mention. Not only did I encounter Paul for the first time on the charcoal project early in World War II, and as Libby's supervisor on the Manhattan Project phase, but when I, at the end of the Pittsburgh to work on synthetic fuels research. Paul was already in Pittsburgh in charge of the Gulf program at Mellon Institute. At that time still separate from Carnegie, was not Carnegie Mellon. So we had a third means of contact. My detailed exposure to catalysis was in a continuation course, ACS, that Paul gave at the University of Pittsburgh in my first year in Pittsburgh. Wonderful course with notes. Paul also was very influential in helping me, unaided by my supervisor at the University of Chicago, my thermal prof, who nominally was in charge of the charcoal project at Chicago, but did nothing about getting the work that I did declassified. And I understood later was angry that I had done it and went ahead with publishing an article, getting it declassified and accepted by JACS, I think. After he refused even to answer my letters and my sending him a manuscript before sending it in to the journal.
You want to name him?
Yeah, T.F. Young, who himself was a student of Jan Lewis from Berkeley, and a very fine thermodynamicist, but we refer to the Shakespeare tragedy, where everybody dies at the end. Where the hero postpones doing anything to avenge the death of his father. Young was somebody who didn't proceed with things. I think Irving Klotz, who has retired from Northwestern and was earlier my lab assistant when I was a grad student at Chicago, and I worked with Irv a little at Northwestern during the war years. He had trouble getting his PhD dissertation published because Young was so dilatory about doing anything. By contrast, my man, Frank, got my dissertation published in the same year as I got my PhD in 1941. I was 22 at the time still, and insisted that I be the senior author, which means the first author was Weller and Frank. It was all his ideas, actually. My role models were Frank and Emmett. Noblemen, salt of the earth kind of thing. And Livy I never had affection for. Respect in some areas, surely, but not a man I chose to model myself to. And I'm not sure that I ever came close to either Frank or Emmett in nobility. Emmett, I knew how much he had done for me. He rounded me up as an author of a chapter for one of the volumes in the Emmett series on catalysis at a time when I was already at Hoodry, Philadelphia. And his wife told me privately once I was open in my admiration for Paul, and she told me how much she knew of the many occasions when he assisted with money, young people who needed help, and he did it always in an anonymous way. Some first-class people, and you can't imagine yourself being like that, but I would hope at least while I was a teacher of graduate students at the University of Buffalo, that as a father figure for them, and I was old enough to be the father of all of them, they got something of this flavor. But Emmett was my real contact, and Libby, my supervisor, let it be.
Who were some of the other people in the group at Columbia at that time?
Well, I had to interact in almost every place I was with people in different groups. Bob Kunin, Kunin, became a guru in the ion exchange field, and the amberless resin fields after World War. And I first met Bob in the Manhattan Project, and he ended up in Philadelphia as I did in the 50s. So we saw each other in families at the time. Al Grenall was very helpful in doing X-ray crystallography at the time, and I became somewhat adept when my eyes were better and I was many decades younger, in seeing faint lines in X-ray film. There was no counter kind of thing available at the time. So one learns when it's a hands-on operation at that time. But in terms of interaction, especially in the Manhattan Project, the project was so compartmentalized that it was only by chance that I learned of Zachariason's work at Chicago, for instance. We were not given progress reports of anybody else. I must say, I was so young then, still in my early to mid-20s. I was terribly naive then, and unimaginative, I must confess. I'm not that much better now, but I've lived more years.
Did you interact with Yuri at all?
No. I'm not sure I met Yuri, but Alex Mills, my direct supervisor and director of chemical research at Hoodry, who became, as you know, very important in DOE, had been a student of Yuri, got his doctorate under Yuri, so I was familiar with that. At Hoodry, I met Hoodry socially at a party in his house, but the year before I joined Hoodry, 1950, Hoodry, for financial reasons and competition from Esso or Exxon now in catalytic cracking. Had become financially embarrassed, I guess, and was compelled to dissociate himself from the Hoodry Process Corporation with lab in Marcus Hook, PA. So I met him at a time when I couldn't appreciate the kind of, as Alex Mills expressed it to me, intuitive genius he was. And I will mention, in case you don't have this on record, an episode between Mills and Hoodry, Eugene Hoodry. At least Mills was aware of this. During the early years of the war, when the access to natural rubber was in the Pacific was cut off by the Japanese, Hoodry realized by that time that if we had a route to butadiene, that synthetic rubber was going to be a possibility. Where do you get butadiene? Well, the largest precursor, most available precursor was normal butane. So Hoodry said, why don't we just dehydrogenate butane to butadiene? Now you have to have fairly extreme conditions of temperature because the equilibrium is lousy. So it's like 600 Celsius and so on. And 10-minute cycle time, 4 minute on stream, 1 minute for regeneration, 4 minute, for purging, and 4 minute for regeneration, and so on. A mess. And low pressure. And a catalyst. What catalyst? Well, you have to invent. It's not known at that time. Well, apparently, according to Mills, Hoodry thought for 30 seconds and said, well, we'll use alumina as a support, and chromia should be a good catalyst for the reaction. What concentration? Well, try 20% chromia on alumina. And the next day or whatever, it was tried and it worked. So I learned at this meeting that the Hoodry name still exists as a division. I thought it had disappeared from Air Products, but no. And they're still using 20% chromia and alumina as a catalyst with promoters. That's okay. After, 55 years. So this was the kind of intuitive genius that Hoodry had. And one famous meeting I had, not professional, was with Enrico Fermi. And under odd circumstances. Under the stands at the University of Chicago, this was after World War II, and not where the pile was built by Fermi and co-workers. There was an ice skating rink. And in the early 50s, visiting my wife's sister and brother-in-law, my brother-in-law by marriage too, on the rink, the brother-in-law, who was a distinguished, now retired, virologist, was Italian by origin, but he fought in the U.S. Army and graduated from Chicago himself, and knew Fermi. So it was a case of bumping into somebody on the ice and introducing me to Fermi. Well, I knew enough about Fermi at the time. I know more in everything honorable and glorious and wonderful to be overcome with pleasure at the meeting. And a genial, shortish guy, balding, shortish. He was about my height. But that's one of the close approaches to fame, aside from working with a Nobel Prize winner, a great man. And at one time, as a graduate student, I explored with Robert Mulliken, not Millikan, but Mulliken, who was a physical chemist originally, but turned to spectroscopy and taught in the physics department at Chicago. I was always interested in physics from high school on, and kind of torn between chemistry and physics. Did it make sense to include physics as a major or co-major? And he said it was too late, and properly so. Malkin thereafter again received the Nobel Prize for his work on the nature of the chemical bond, quantum mechanical. I had him one summer in 8 o'clock class in Chicago in what I would describe as summertime Baltimore weather, in a class in molecular spectroscopy. And he was one of the, if not the worst lecturers in my career. But again, these were all wonderful experiences for me to have. I never felt that going to Harvard or Yale or whatever as an undergraduate was all that important. Wayne was not a first caliber or school, but I was as well prepared in chemistry as the people whom I met as classmates as a grad student in Chicago, who themselves had their BS from Chicago. But for graduate school, being exposed to really great minds is important and useful throughout one's life. But as Chicago, in terms of physics, I took many graduate courses in physics, for credit even, and loved it. And I sat in to one or two graduate courses in math, survived, and the virtue of these things is you're never so frightened in later life when you come to having to make use of these disciplines. For instance, in Pittsburgh, while I was nominally in charge of laboratory and bench scale coal liquefaction research, it was suggested to me that it might be interesting to look at the separation of gases by fractional permeation through a thin organic membrane. Nothing existed in the literature at that time. So we did the first experimental work in the laboratory in enriching air as much as 40% oxygen from 19-something in normal air. And I worked out the theory for two limiting cases on the tail side of the membrane, one of which was for no mixing, which is plausible, and involved the solution of to me, differential equation which I had never seen before. And that was published and really it was a pioneering work in a quite separate field. Also at the Bureau of Mines at that time, since I had friends in the organic chemistry section, I worked with a man, Calvin Golumbic, who had a counter-current distribution apparatus for separating things. And I worked out the difference, not differential, but the difference equation to permit determination of the acidity constants for a number of aromatic carboxylic acids which occur in coal liquefaction products. And this kind of thing, I think, would have frightened me off from doing anything if I had not exposed myself to some courses in math beyond calculus or differential equations.
Did you encounter Sir Hugh Taylor at the Columbia project?
Not on the project. At NYU, where I was a postdoc, his younger brother, H.A. Taylor, Austin Taylor, was a professor there, and I knew him. And he also was interested in something that I later became more interested in, the kinetic behavior for adsorption. But Austin was never the penetrating intelligence in chemistry that Hugh was. Hugh Taylor was a major force in catalysis, historically. He was also one of the few difficult people that I ever encountered, not because of personal encounter with him, but I remember at an early ACS meeting, maybe in 1943, some young person, maybe a graduate student or a young faculty member, was giving a paper which was so-so, but like most of them. Taylor, in the audience, stood up and gave a devastating critique of the whole idea and the procedure of what this young man had done. I can't really imagine how the presenter felt, but he must have been destroyed by having somebody of Taylor's stature in public condemn him for ignorance or worse. That's not the kind of thing you do when you're a great man and you have somebody defenseless before you. But Michel was always very devoted to Hugh. I remember when Hugh Taylor was, I think, in his 80s. I'm not quite there, only 78. Was brought up from Princeton by Michel to attend the Gordon Conference on catalysis. Not that Taylor had any contribution to make at that stage of his career, but the devotion was always there, and I have to be impressed by that. For my money, Boudard is just as important as Hugh Taylor in our story of catalysis.
Did you run into Ray Christ while you were at the Manhattan Project?
I can't remember if I did or not. How do you know Christ?
Indirectly through Emmett's files, and I just made a video of him about a month ago.
Christ?
Yeah, 96 years old.
Yeah, Chris, I think, was the top man in the Carbide organization. Is that correct?
That's right.
Now, Carbide took over that branch of the Manhattan Project that had started, as I did, at Columbia University. And we were in some uptown building not too far from, Harlem. Just, Carbide was never, and maybe not even today, my favorite industrial organization from the standpoint of caring about their employees. And I always attribute the kind of people you encounter in an organization to management. So I guess I associate the name of Chris with my kind of gray image of Carbide as an organization. My wife and I were discussing about this hotel, the Hyatt, how nice everybody in the waitress or somebody at the front desk has been, without exception. And I was sure that this reflects Hyatt management, and we're impressed by that. Henry Storch created that kind of atmosphere at the Bureau of Mines, my time there. And Alex Oblad also at Hoodry, and Alex Mills, of course, who remains a good friend, close friend, even if we see each other by correspondence, mainly, except for meetings.
Now, how do you describe the Bureau of Mines at the time you were there?
It was not only the preeminent, but close to the only laboratory in the U.S. doing basic research on synthetic liquid fuels, along with other things in other divisions. There was an explosion division interested in explosions from coal dust in mines and so on. Lewis and von Elda were great names in that area. So nowadays, many of the national laboratories are involved in coal research, but I think that was a matter of survival after the war, what to do so we don't have to fire people. But in the 1940s, late 40s, when I was there, 45 to 50, I can't think of any other place that was doing the kind of work that was being done in Pittsburgh originally, and then at Brewston when the labs at Brewston were built in 47, and we moved out. So it was a great place, and especially under Storch. And Bob Anderson ended up first in charge of the Fischer-Tropsch research, and then as director of the whole establishment. And then Sun Chun took over when Bob, after I moved to out of the Bureau, he moved to academia in Canada. And there was a loss to catalysis. We were tennis partners during our years at the Bureau.
How much did the people at the Bureau utilize what was learned in Germany following the war?
Oh, a
of
great
the German
deal,
records?
a great deal. And we had, thanks to the teams of people that visited the Matthew Pier's work, for instance, extensive reports which still may exist in people's minds nowadays, but from my experience, anything before 5 years ago is forgotten in literature. So these were available to us, and a couple of German scientists were brought to the Bureau in Pittsburgh, and we had the benefit of their knowledge. Donath in coal research, for instance, was there, and his knowledge of the history of liquefaction was wonderful, and the chapters he wrote in various treatises afterwards, the Eliot book, and so on, were very helpful. So we had the benefit in this country not only of the rocket scientists, but of the chemists and chemical engineers, I must say, from Germany, and mainly from Germany. I can't remember. Well, work had been done extensively and before my time at the Fuel Research Board in England, but not in the systematic way that appealed to me for my work on mechanism, which was basically untouched by them, and not much of a comparative catalyst study to understand the role of a given catalyst in the mechanistic treatment. I'm not sure it's well understood to this day, but I can ask what is. It's not just coal liquefaction.
Now, what was Storch's management style?
Well, I can only comment about our direct interaction. Storch, there was mutual respect between us. I liked him enormously. He was so easy for me to get along with, and I must have been a chore for him. About once a year, he would bring up this idea. Now, tin catalysts, especially with a halogen acid, is one of the best catalysts for primary liquefaction of coal. And there are organo-tin compounds like tin tetraethyl, in principle available. Why don't we try that, he would come to me. Because the decomposition from the vapor phase will give very fine dispersion of the metal. And already I had shown from studies of different methods of introducing tin into powdered coal that the catalyst dispersion was enormously important. And I told him the liquefaction conditions involve not only high pressure, but temperatures of 400 to 450 Celsius. And the organo-tin compounds just decompose if you look at them askance. It will never survive. And he, in essence, said, okay. And we never tried that. He didn't heckle me or argue with me. And the group that I was in charge of came up with a lot of stuff and many publications. So he was not disappointed, I'm sure. And he and my direct supervisor, who was in charge of the coal liquefaction section, Zeke Clark, marvelous chemical engineer, but not chemist or physical chemist, were encouraging to me to take on as a part-time sideline this separation of gases by diffusion through membranes, which was successful. And I remember doing longhand with a slide rule, multi-stage separation of, say, methane from natural gas, or hydrogen from recycled gas, or helium from natural gas, laboriously through a 5-stage separation, and published in Chemical Engineering Progress, my first publication in the Chem Engineering Journal, 1950, I think. I got a prize for the best presentation at that meeting. Amazed me. So everything panned out, and all of my experience, I have to say this. Surely after World War II, which was a traumatic time for everyone, were such that I think, even knowing what I do now, if I had my life to live over, given the circumstances that existed at each period, I would do in the same order Bureau of Mines, Poudre, the Ford experience in California, and teaching. I would do over in the same order without change. I have been blessed in my lifetime, and the wisest thing I ever did was proposing to my wife, and she accepting. We decided to get married 10 days after meeting. My supervisor, my mentor at Chicago, was aghast. It will never last. We have celebrated our 53rd anniversary so far. It won't last forever, but only because people don't. So we have had a very rich life and happy life, regardless of, I'm not treating physical problems, which have been severe. Fini.